So before ending this chapter, I'd like for us to have some fun. And the way I'm going to do this is I'm going to look at a difficult problem, a difficult integral, but instead of us doing the hard work, I'm going to let the computer do it, okay? So I'm going to focus on the physics and the result. And the computer is going to do the hard work. I will also show you how to ask the computer, please, can you do this difficult integral for me, okay? So we are going to focus on this example, which is Ampere's law. Ampere's law is this law here. So Ampere's law says that the circulation of the magnetic field on any path C that is closed, that's why this is a circulation. So for example, this path, this potato path here. So the circulation of the magnetic field turns out to be equal to mu0, which is a constant. It's called the permeability of free space, times the enclosed current, the current enclosed by this path. So whatever current crosses this surface, that will be the enclosed current. If you have several currents, for example, you have one here, and one here, you just have to add the three currents, okay? So theoretically, I'm sure you are all familiar on how to apply this to very simple cases, such as a single current carrying wire. But here I want to do it in a complex case like this, where I'm going to have two wires, one is placed here and the other is placed here. They are going to have a different current each, okay? And I want to calculate the circulation of the magnetic field around the path that includes both wires, okay? So the aim is to see if I can do this integral in the computer and find that the result of that circulation is equal to the sum of these two currents, okay? So the first thing I need to do is to calculate this magnetic field, which you can see is beautiful, right? You see, like, clearly this is counterclockwise, which means that following the right-hand rule, this means that the current is coming outside of the page. And then here we have clockwise rotation of magnetic field, which shows that the current on this wire is going into the page, okay? So when calculating the total current, we will have to subtract the two currents because they are opposite. We can also see that the magnitude of this current is clearly bigger than this one, right? Because this current is kind of eating the other one. You can see, yeah? This is a much weaker magnetic field created by this wire. So my first step is going to be calculating the magnetic field. And that's actually surprisingly easy. We are going to start with the known equation for the magnetic field of a single current carrying wire, which is given by this expression. And this expression has the current carried by the wire and then rho, which is the distance to the wire. Okay, so the square root of x squared plus y squared, assuming that the wire is at the origin. And then this is multiplied by e phi hat, which is the unit vector in polar basis, in polar coordinates. So the first thing I'm going to do is, since I want the currents to be placed not at the origin, I will not be able to use rho and phi anymore. I will not be able to use polar coordinates. So I want to change everything into Cartesian coordinates. So first, rho is very easy. I change it to the square root of x squared plus y squared. And then e phi hat, if you look it up on a table, this is the expression for e phi hat, but I want it in rectangular coordinates. So you can calculate the sine of phi by doing the famous triangle where you have x, y, rho, and phi. So clearly the sine of phi is y divided by rho, which is y divided by the square root of x squared plus y squared. So the minus sign is minus y divided by the square root. And then the y component is the cosine, which is x divided by rho. So you have x divided by rho. Okay, so all this is just e phi hat. And now we can multiply this square root by this one and simplify things like this. Okay, so this is the current, is the magnetic field created by a current created from a wire located at the origin. Okay, and this is a known equation. So this is going to be our starting point. Now, what if I move the wire and instead of placing it at the origin, I place it at some other coordinate x1 and y1? Well, that's very easy. I just need to change wherever an x appears, I change x by x minus x1, and wherever y appears, I change y by y minus y1. This is like translating the whole function, right? So if you do those substitutions, you end up with this expression for the current, for the magnetic field created by a current. The current is equal to y1, and it is located at coordinates x1, y1. Okay, and this is the magnetic field of this current. So now to calculate the magnetic field of the two currents, I just need to add that magnetic field twice. So I add this expression for a certain value of x1, y1 and a certain value of the current, plus another copy of that expression using different values for x1, y1 and for y. Okay, and this will give me some total magnetic field, and I can do this sum easily using Mathematica. So here I clear all of the variables. I assume that x, y, z and phi are real numbers. This allows Mathematica to simplify things. And now I start with the known expression for the magnetic field of a wire, which depends on the position vector xy, on the current y1, on the current I1, and on the position of the current, which is x1, y1. Okay, and this is the expression we just found for a single wire. And then what I do is that the total magnetic field, which is a function of position, depends or is equal to the addition of two copies of this thing above, with the difference that the first wire is going to have a current of 1, and it's going to be located at x1 equals 0, y1 equals 1/3, and the second wire is going to have a current of -0.5, and it's going to be located at position x equals 0 and y equals -1/3. So then I add those up and I simplify, and I get the result. So this is the magnetic field produced by the two wires. So now I can plot it. I use this command called vector plot. I give you b of xy, I say x between this and this, y between this and this, and then some options, and this plots the magnetic field of the two wires. Okay, so you can see how simple it was. Notice that we could change the current of the wire. For example, we could make the second wire have a current of +1/2 instead of -1/2. So then this changes the magnetic field, and if we plot it now, you can see that this is now different. So now clearly the two wires, the two currents are both of them outside of the paper, outside of the screen, right? And there is like a net circulation of the magnetic field around them. But let's return to the case -1/2, which was the case I was plotting in the notes. So here you can see how the two currents seem to be opposing. So the magnetic here wants to go clockwise, the magnetic field wants to go clockwise here, and it wants to go anti-clockwise here. And all of this is contained in this simple sum of two terms. Okay? So that was the easy part. Now let's do the integration. So I want to integrate on a circular path. So remember the steps to calculate the circulation. First step, parameterize the path. So my vector r path as a function of phi equals cosine of phi, sine of phi. You know the drill. And that's going to be the path. Then I calculate the differential vector dr. And that's given by the derivative of the path with respect to the parameter. Yeah, so this is the path. And I calculate the derivative with respect to p. And this just means that I'm going to substitute this variable that I called p by the variable phi. It's just a way to make sure that dr is a function of phi. And this gives me, so this first line has the result here, that is the path, and then this second line, which is dr, has the result here. And you can see that this is the derivative of that. Yeah. The third step was to calculate the integrand. And remember, you had to do two things. First, substitute the equation for the path into the magnetic field, and that is achieved here because I do b, instead of saying b of r, like I did here, b of xy, instead of doing that, I'm doing b of r path of phi. So I'm substituting these two values into b. So x will be cosine phi and y will be sine phi. That's there. And then I'm doing the dot product between, so the dot product between that and the differential dr vector. Okay, so I do the dot product and I simplify, and I end up with this. So this is going to be my integrand. So if we go back here, b dot dr is equal to this, which is what we just saw in Mathematica. So this is now the integrand. So now the only step that is left is to integrate that, and the parameter is d phi, so we just have to integrate that between 0 and 2 pi. Okay, so we are going to do the integral of the integrand. And the way we do that in Mathematica is very simple. We say integrate the integrand from phi equals 0 to 2 pi. And Mathematica tells us 1/2. So that concludes the calculation of the circulation. It says 1/2 and not 1/2 times mu 0 because I ignored the mu 0. I didn't add mu 0 into the magnetic field because it's just a constant, so I left it out. But if I had included a mu 0 here, it would also have been in B, a mu 0 multiplying everything. It would also have been in the integrand, a mu 0 multiplying here, so I would have gotten a final integral of 1/2 times mu 0. So does this make sense? Well, yes it does, because this path includes a current of +1, which is located here, and a current of -1/2 included here. So the total current is 1 minus 1/2 equals 1/2. So that's why the circulation was 1/2 times mu 0. Okay? So I hope you can see how magical that is, that this apparently difficult integral, because you notice that the magnetic field is at a certain angle with the path. At each point the angle changes, yeah? So the magnetic field's angle changes with respect to the dr. And yet when you do the circulation throughout the entire path, the result only depends on the currents that are inside of the path. So I think that's quite magical. And in the live session we will test with different paths and we will see the results. Okay? So thank you very much. I hope you enjoyed this chapter. See you in the next chapter or in the live session. See you.